Hi everyone. Today I will present my work on an attack that leverages DNS tunneling to covertly transmit HTTP requests and responses. So domain name system or DNS servers translates a readable domain, host name used by, into addresses that can be read by machines. And DNS tunneling is a type of cyber attack that allows hackers to bypass network security by using the DNS as a transport for malicious traffic. By hiding non-DNS traffic within DNS packets, attackers can often bypass network security measures. The image shows this, where an attacker steals sensitive data, such as passwords, by using DNS queries. So the attacker first registers a malicious domain and configures its authoritative DNS server. A compromised machine, infected with malware, will encode sensitive data into a subdomain and send it via DNS queries. These queries travel through a recursive DNS server and reach the attacker's authoritative DNS server, which extracts the embedded data. So this method bypasses traditional security measures by disguising data as legitimate DNS traffic. So the danger of this attack is significant. Since DNS is a fundamental protocol that is rarely blocked, attackers can use it to steal sensitive data or bypass content filtering systems. Even when the network is configured to block HTTP or other protocols, DNS traffic is often allowed. This means that the attacker with access to a compromised machine can leverage DNS tunneling to steal confidential information or launch further attacks, all under the radar of standard security measures. So a real-world example would be oil rig. An active threat group targets financial, energy, and government sectors in the Middle East. According to a report by Unit 42, oil rig extensively uses DNS tunneling as a command and control channel for its malware. OilRig employs multiple tools to implement DNS tunneling, as shown on this timeline. So this shows that DNS tunneling is a real threat. So another danger of DNS tunneling is that it can help attackers bypass content filtering systems. We demonstrate this by writing a demo program that runs a whole HTTP proxy service just utilizing DNS. In our implementation, we used Python to create both a client and a server that demonstrate this attack. We divide the attack into 5 phases. First, we encode HTTP requests, then segment it into DNS queries. The client sends all those DNS queries to the server, and the server reassembles segments and decode it to its original request. The server will then forward HTTP request and get a response. The server then encodes response and segment into DNS responses. The server then sends those DNS responses one by one to client, and client reassembles the response and display it. And without further ado, let's jump into live demo. Okay, so this is the GitHub main page of the project. So this implementation consists of 3 parts: a client that runs from the command line, a proxy that acts as a HTTP server and forwards all HTTP requests, then the actual DNS tunnel server. So let's boot up a demo service on localhost at port 9953. Then we have a demo site. It receives a post request, parses an attached file, and replaces certain punctuations in the text right here. And then it returns the modified text as a response. So I add some payload to the HTTP request and response to show that the full potential of the DNS tunnel. Now let's run client. In the client.py, we connect to a localhost DNS tunnel Then we send a post request to the demo server at port 7000, and we add a payload demo.txt, apart from famous opera Hamlet. Okay, so the program finished running, and you can see the HTTP requests and responses are sent over DNS. Now let's open up Wireshark to see the network activity. Let's run the client again. And yes. First, the client generates a random record ID for reference. Then the client sends multiple DNS queries and sends the actual HTTP request contents encoded in base 32. The client will send a trigger request and the server will begin to access the internet. Then the server will begin to respond in multiple DNS requests. Now let's see that in the first response, the server will tell the client how many segments are there in the response, and the client will continue to send multiple queries to retrieve all the segments. So as you can see, these 13 more. And then the client will compose the whole HTTP response and display it. That is the function of client. And now let's see the HTTP proxy. It will listen on a port, and you can go ahead to your Chrome to set your proxy server as the localhost at that port. So I selected a website called httpforever.com. It runs completely on HTTP. Notice that I didn't implement HTTPS over DNS, so that these JavaScript files hosted on Cloudflare won't be able to pass through. So here, as you can see, the traffic have been forwarded into the DNS terminal, and the terminal is running properly. So here, this HTTP request requesting a icon file, which is a binary, is successfully parsed. And the website itself is also successfully parsed. So that's all for the live demo. Okay, so one key decision was to treat the entire HTTP request and response as raw byte arrays. We only parse the header to extract key fields like method, URL, and host, then the body is maintained in its raw form. A major technical challenge was handling the base 32 encoding and decoding. DNS labels are limited to 63 characters, so I had to carefully split and reassemble the encoded data. I also had to ensure that proper padding was applied during decoding. And another challenge was maintaining the integrity of the raw data. By treating the payload as a byte array, I avoid any issues related to character encoding, which is crucial when the payload contains binary data. So this attack teaches us several important lessons about security. First, even well-established protocols like DNS can be abused when security policies do not consider covert channels. Second, the attack underscores the need for deep packet inspection and anomaly detection, even on protocols that are considered benign. And finally, it reminds us that a defense in-depth strategy is essential. Relying solely on traditional firewall rules is no longer sufficient. So defenses against this type of attack include monitoring DNS traffic for unusual patterns, such as long domain lengths, frequent querying, and random base 32-like strings in queries, and employing DNS query logging and anomaly detection systems. So organizations should also enforce ingress filtering and consider using DNSSEC to add a layer of authentication to DNS responses. Further research might focus on designing intrusion detection systems that specifically target covert channels within DNS traffic and improving network segmentation to restrict unauthorized data flows. So in conclusion, the DNS tunneling attack is a potent reminder that attackers can exploit any protocol that is not closely monitored. By understanding how this attack works, we can better protect our networks and develop a more robust defenses. That's all for my presentation. Thank you for your attention.